computer memory and the binary numbering system. A memory device is a gadget that helps you record information and recall the information at some later time. So in order for us to recall something, we put a bow on our finger to recall it. Requirement of a memory device. A memory device must have more than one state. Otherwise, we can't tell the difference. So memory device in state 0, nothing on the finger. Memory device in state 1, a bow on a finger. The switch is a memory device. The electrical switch is a memory device in that you can turn it on and off. It has two states. We will call off state 0 and we call on state 1. Memory cell used by a computer, we have one switch, can be in one of two states. A row of n switches, where n is a natural number, can be in one of 2 to the power of n states. Example, row of 3 switches. Our legend is either off, and in this case, our legend is on. So, possible state that row of 3 switches can assume, none is on. Next switch, that switch is on. For the next, the middle switch is on, the first 2 are off. For the fourth, the last 2 switches are on, the first switch is off. The first switch is on, the other 2 are off. First switch on, middle switch off, last switch on, off, all 3 on. A row of 3 switches can be in one of 2 to the power of 3, which is equal to 8 states. Therefore, we have 8 possible states and are given in the figure above. 1, 2, 3, 4, 5, 6, 7, 8. We saw how information can be represented by number by using a code, which we also call agreement. If you recall, we can use numbers to represent marital status information. 0 for single, 1 for married, 2 for divorced, 3 for widowed. Now we can represent each number using a different state of the switches. So we've got our 3 switches, and our legend here, if it's colored in black, it is on. So 0, all 3 off. 1, the last one is on. Middle on, last 2 are on. For 4, first one on, last one on, first 2 on, last 3 are on. All 3 are on. To complete the knowledge on how information is represented inside the computer, we will now study how to use the different states of the switches to represent different numbers. The representation scheme has a chic name. It's called the binary number system. The binary number system uses 2 digits to encode a number. 0 represents no value. 1 represents a unit value. That means that you can only use the digits 0 and 1 to write a binary number. Example, some binary numbers: 0, 1, 1, 0, 1, 1, 1, 0, 1, 0, and so on. The value that is encoded, represented, by a binary number is computed as follows. Our binary number is D into 1, D into 2, and so on, D1, D0. Value coded by a binary number is D, n minus 1, multiplied by 2 to the power of n minus 1. So those 2 values need to be the same, plus D, n minus 2, multiplied by 2 to the power of n minus 2. So those 2 are the same, etc., 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 1, 1, 0, 0. So let's give you an example. For our binary number 0, it will be 0 multiplied by 2 to the power of 0, which equals 0. For our binary number 1, 1 multiplied by 2 to the power of 0 is equal to 1. Recall, 2 to the power of 0 is 1. 1 multiplied by 1 to the power of 1 plus 0 multiplied by 2 to the power of 0 is equal to 2. Remember, when we have two binary numbers, we are adding the two binary numbers. So 1 multiplied by 2 to the power of 1 plus 1 multiplied by 2 to the power of 0 is equal to 3, and so on. Now you should understand how the different states of these three switches represent the numbers 0 to 7 using the binary number system. We have three switches. This is how they look when they're off, and this is how they look when they're on. So all three off, 0, last one on, middle one on, off, off, on, off, on, off, on. To try to understand this joke, there are 10 types of people in the world. Those who understand binary and those who don't. Now, if you got the joke, there are binary, 1, 0, which is the same as saying two types of people. Those who understand binary, which is numbers, and those who don't. A cute binary number joke, another knockoff, is there are 11 types of people in the world. Those who understand binary, those too stupid to understand, and those who try to lick their elbows. Recall what we have learned about computer RAM memory. The RAM consists of multiple memory cells. Here is your address of your memory cells, 0, 1, 2, 3, and this is your RAM. 13, 3, 0, 45 are stored into each one of these different memory cells. Each memory cell stores a number. Now, the connection between the computer memory and the binary number system is the computer system uses the binary number encoding to store the number. So how we perceive it is, here is our address of our memory cell, 0, 1, 2, 3. Here is our RAM, which is our memory, 13, 3, 0, 45. So the reality is the address of the memory cell, which is 0, 0, 0, etc. to 0, 0, 0. And each byte has 8 bytes. 1, 2, 3, 4, 5, 6, 7, 8 bits, which makes a byte. Now a memory address is 32 bits long. That is how long the address is. So note that the address is also expressed as binary number. A computer can have over 4 trillion bytes, so 4 gigabytes of memory. So we need a 32 bytes to express the address. Now a computer is an electronic device. So the structure of the RAM memory is used by a computer consists of a large number of electronic switches. So the switches are organized in rows, and for historical reasons, the number of switches in one row is 8. So, give you some details. In order to store text information in a computer, we need to encode 26 uppercase letters, A, B, and so on, 26 lowercase letters, A, B, and so on, 10 digits, 0, 1, and so on, 20 or so special characters, like your and, your percentage, your $sign, and so on, for a total of about 100 different symbols. The nearest even power to 2 to the power of 9 that is larger than 100 is 2 to the power of 7, which is 128, which is greater and equal to 100. For a reason beyond the scope of this course, an 8th switches is added. In this portion of the RAM memory looks like such. We've already discussed the memory addresses here, which has to be 32, and our RAM memory, which is 8 bytes, which makes a bit. But information is stored in the RAM memory depends on two things: the type of data. This is the context information. So example will be your marital status, your gender, your age, salary, and so on. This determines the encoding scheme used to interpret the number. So as I've said before, a bit is a binary digit, a smallest memory device. A bit is in fact a switch that can remember 0 or 1. Now the digits 0 or 1 are used in the binary numbering system. A byte is 8 bits. A byte is in fact one row of RAM memory. A kilobyte is 2 to the power of 10 bytes, approximately 1,000 bytes. A kilobyte is approximately 2 to the power of 10 bytes, so 1,024. A megabyte is approximately 1 million bytes. A gigabyte is 2 to the power of 30 bytes. And of course, we get a terabyte. Now, to understand this concept of bytes better, let me put it into perspective for you. A single byte is equal to one single character or letter of the alphabet. So I'm going to write A here. All right. Now, a kilobyte is 1,000 letters. So 1,000 letters, or roughly 150 word essay. That is a kilobyte. Now a megabyte is 1,000,000 letters. And here is where you guys get lost. Now, have you ever seen 1,000,000 of anything? Now, if you had to bring 1,000,000 rand in 1 rands for homework to class, would you be able to fit 1,000,000 rand in the class? What about $1,000,000? Would you be able to put that all in the class? A byte has 8 bits, and therefore it can store 2 to the power of 8, 256 different patterns. So these are 256 patterns are 0000000000001, 1 0 at the end, double 1 at the end, so on and so on and so on until we get all ones. Now each pattern can be encoded exactly one number. So it's encoding one number. All zeros is 0. All zeros except the last one is 1. All zeros 1 0 at the end is 2. All zeros 1 1 is 3, and so on. 250 to the 250 number. Therefore, 1 byte can store one of 256 possible values. You can store the number 34 into a byte, but you cannot store the number 456. Therefore, that's when the value is out of range. That is where int double long comes into handy when you work with numbers in Java. All right, some exploratory stuff. All right, a computer program illustrates the effect of the out-of-range phenomenon. If you type this into your IDE, you will see that we will have an error. It will call an overflow. Now, memory does not have enough space to represent the value. This is the same phenomenon when you try to compute 1 divided by 0 with a calculator, except with a calculator, it was programmed by the manufacturer to report an error, and the computer is not. Now, the computer can combine adjacent bytes or memory cells and use it as a larger memory cell. Systematically, you got 2 bytes and 1 16-bits memory cell. A 16-bits memory cell can store one of 2 to the power of 16, which is 65,536 different patterns. Therefore, it can represent larger numbers ranging from 0 to 65,535. Now, example, how a computer can use 2 consecutive bytes as a 16-bits memory cell. Here is your address of the memory cell, and here is your RAM, your memory, and if you had to try and find 3,331, which is a decimal, it would look as such. Can you see how programming in the 1940s, how difficult it actually was, because they had to memorize all of these numbers. The bytes at address 0 and address 1 can be interpreted as 16 bits memory cell with address 0. Now, when the computer accesses the RAM memory, it specifies the memory location, its address, and the number of bytes it needs. Now, the computer can also combine 4 consecutive bytes and use them as a 32 bits memory cell. Such a memory call can represent numbers ranging from 0 to 2 to the power of 32 minus 1, which is a large number. I can't even say that. You can also combine 8 consecutive bytes and use them as a 64 bits memory cell. Such a memory call can represent numbers ranging from 0 to a huge number. There is no need today to combine 16 consecutive bytes and use them as a 180 bits memory call or memory cell. But this may change in the future, which we are already seeing now. If you download a program, you can download it for 30 bits, or you can download it as 60 bits. You can see already now it's already changing this future. You can see when you download a program, you can download it as 32 bytes or a 64 bytes program. Now we've discussed the difference between a 32-bit and a 64-bit hardware. Now, how does that affect our software? Generally speaking, a 32-bit programs can run on a 64-bit system, but a 64-bit program will not run on a 32-bit system. Already around 2008, a 64-bit version of Windows and OS X became standard, and 32-bit versions were still available. So therefore, if you bought your computer into 2009 or later, there is a good chance you are running a 64-bit operating system. Hopefully, this explanation has given you a better understanding of what 32-bit and 64-bit means, as well as the computer memory and how the binary numbering system actually works.